Let's get right into case study 11, GNN plus XGBoost. We're tackling a classic systems engineering problem today, which is anticipating a supply chain collapse before it actually happens.
Here's the scenario. A severe storm hits a critical manufacturing region. The emergency operations center is scrambling. Now, the immediate damage, that's obvious. But as a systems engineer, your job isn't just to report the news. You need to know not just who is failing right now, but who is going to go dark next month because their upstream partners collapsed. You have to map the contagion of disruption. This perfectly illustrates the gap between standard engineering approaches and a network-aware approach. The naive approach, the one most engineers reach for first, relies entirely on flat tables of individual supplier metrics. You look at a supplier's own historical delay rate, maybe their capacity, their region. But we're going to build a network-aware approach. We are going to measure the structural risk hidden upstream by looking at the delay rates of your supplier's suppliers. And that brings us to the fourth professional skill in our course framework, predict. In the previous labs, we've identified networks and measured their structures. Now we're actually forecasting node-level outcomes. We're going to take a node's structural neighborhood and turn it into mathematical features. Specifically, we'll create embeddings via graph neural networks and feed those right into a machine learning model to predict supplier failure. But before you touch the interactive tool or write any code, you're going to pick up a marker. It's time for the sketchpad moment. Remember, in this course, the thinking happens on the sketchpad. The tool is just there for verification. Before running a complex algorithm, you need to mentally and visually map out the system by hand on your notebook page. So grab your sketchpad, you'll sketch a focal node in navy ink, and then draw directed edges branching out to its upstream neighbors. Those are the suppliers feeding it. Then branch out again to their suppliers. Take a good look at that two-hop neighborhood. Grab a mustard yellow marker and highlight any single-source vulnerabilities. You'll see clearly how structural risk is inferred directly from the neighbors. You're doing manually exactly what the graph neural network will do mathematically. Once you've mapped that logic out by hand, you'll open the interactive lab simulation in your browser. You'll be looking at a synthetic supply chain with 22 supplier nodes and 38 directed dependency edges. The node size encodes degree centrality. You'll also have a slider to step through 12 monthly temporal snapshots. Take your time here. Seriously, slower is better. Watch how the disruption risk physically migrates through the network, moving from upstream nodes down to the final assemblers, month by month. Notice how we translate that visual risk into machine learning features. Compare the two types. First, you have your raw tabular features, things like a supplier's tier, region, and their own historical delay rate. Then you have your GNN embeddings. For this, we use a parameter-free graph convolutional network aggregation. What that means is your embedding is essentially the average lag rate of your one-hop and two-hop upstream neighbors. While you're working through the interactive lab, you're going to hit a specific learning check about a node named Shenzhen Fab. Now, Shenzhen Fab has an excellent historical delay rate of just 0.04. If you look purely at its own tabular data, it is a perfectly healthy supplier. And yet, the network flags it as highly likely to be disrupted next quarter. I want you to investigate its upstream edges in the simulation to find out why. I'm not going to give you the answer here. You'll figure that out yourself when you trace those edges backward. After that interactive simulation, you'll move right into the coding exercise, working with a dataset of 500 suppliers over 52 weeks. If you're on the Python track, you'll build the full pipeline. You'll feed raw features, lagged features, and those GNN embeddings into an XGBoost model, achieving an ROC AUC of roughly 0.66. Now, because R currently lacks a primary GNN library, the R track skips the embeddings entirely. It runs XGBoost only on raw and lag features and gets an AUC of roughly 0.64. That 0.02 AUC gap, that is not just a rounding error. That gap is the precise, quantifiable predictive value of the network structure itself. We're dismantling one core misconception today, and I really want you to remember this sentence. Network structure is a mathematical feature, not just a picture. A supplier's individual performance metrics simply cannot outrun its structural exposure. No matter how perfectly a factory operates inside its own four walls, if it sits at the confluence of fragile, sole-source upstream dependencies, it's a high-risk node. The GNN captures that. A flat spreadsheet completely misses it. And that brings us to your final task before you start the lab. Grab your notebook and work through this sketchpad prompt. I want you to draw a supply network of your own design. Pick one focal node and highlight its two-hop neighborhood. Now, ignore that focal node's own data entirely. Write a one-sentence disruption prediction for that node based only on the features of its neighbors. See if you can beat the naive approach by hand.